Hello everyone, I am Rémy Garcia from University Côte d'Azur, and I will talk about a branch and bound algorithm to rigorously enclose the round-off errors. So first, let's see what exactly is an error. Here, you have a function computed over real numbers. It is continuous and has an infinite number of values. Now, let's compute the same function over floating point numbers. What we get as a result is a discrete function represented by a finite set of points. But even though both functions have the same shape, we can see some big differences between them. So let's focus on the blue square here to see them more clearly. Here you have in orange the distance between a computation done over floats and the equivalent computation done over reals. It is what we call an error. An error is computed for a given input by doing the difference between the result of the computation done over floats and the result of the computation done over reals. A particular error of interest is the one shown here in pink. We call it the largest absolute error. It occurs for a given input interval given to our function in the worst possible case. In other words, it is the greatest error reachable in absolute values. Now, the focus of our work is to provide an enclosure of the largest absolute error. To do so, we'll compute an under approximation of it and provide input values to make sure it is reachable, while we will also compute an over approximation of errors. Computing such an enclosure can be seen as an optimization problem, where we will maximize the under approximation of the largest absolute error. But how do we solve this optimization problem? We start with a model representing the problem we want to solve, and we will give it to our solver Fera, more particularly to the branch and bound algorithm. This algorithm can be divided in two parts, the bounding and the branching. For the bounding part, we first compute an upper bound, which is the over approximation of our enclosure, without constraint filtering. We'll also compute the lower bound, which is the under approximation, with a generate and test. We'll randomly instantiate variables to make sure the error is reachable. We'll also use a local search to explore the search space and try improving the computed lower bound. Once both bounds are computed, we now have an enclosure of the largest absolute error. The next step is to go to branching. First, we need to generate sub-boxes from the current box, and finally select a new box in the list of available boxes to explore. Now the whole process repeats itself until there is no boxes to explore. We now have the best enclosure we can compute of the largest absolute error, and we will output it as a solution alongside the input values for the lower bound. Hello everyone, I am Rémy Garcia from University Côte d'Azur, and this is a joint work with Claude Michel and Michel Rueher. I will talk about a branch and bound algorithm to rigorously enclose the round-off errors. But first, let's see what exactly is an error. Here, you have a function computed over real numbers. It is continuous and has an infinite number of values. Let's compute the same function over floating point numbers. What we get as a result is a discrete function represented by a finite set of points. Now, if we display both of them, we can see that they have the same shape. But there are some big differences between them too. So let's focus on the blue square here to highlight them. Here, the distance in orange is the distance between a point computed over floats and the equivalent point computed over real numbers. It is what we call an error. It occurs for a given input, where the result over floats and the result over reals differ. A particular error of interest is the one shown in pink. It is what we call the largest absolute error. For some given input interval of the function, it is the biggest error that our function can reach. There exist many tools that focus on providing bounds on errors. Some even provide bounds on the largest absolute error. So let's see how they do it. Tools like Experimentation FPBench or Precisa compute an over approximation of errors. This upper approximation of errors tells us that errors can be less or equal to it, but never greater than the over approximation. But the computed bounds of errors are still rarely reachable. we don't know if we are close or far away from them. There are other tools like S3FP or FPSDP that compute an under-approximation of the largest absolute error. Still, they can suffer from possible over-approximation of bounds, which is even worse when the under-approximation is greater than the over-approximation computed by other tools. This means that the under-approximation is wrong. Now, notice that none of these tools can compute both an under-approximation and an over-approximation of errors. This is why we want to provide an enclosure of the largest absolute error. To do so, we'll first compute an under-approximation of errors and provide input values to make sure it is not over-approximated and it is reachable, while also computing an over-approximation to have an upper bound of errors. An enclosure of the largest absolute error is our objective. But let's see a motivating example on how it happens in practice. If you consider the following piece of code on the right, first, we compute an expression from 3 input variables and store its result in a variable z. Then, we have a classical control command code, where in the then branch we will proceed as usual, whereas in the else branch we will raise an alarm, because the computation of z has produced some errors. Note that in the conditional we have a variable delta. It is a variable manually set by the programmer that represents the tolerance to errors. We can analyze this code by asking the following question. Is the error on z small enough to avoid raising the alarm when the value of z is less than or equal to 10 over reals? To answer this question, we will consider computation done over double precision floating point numbers. We will take the following input ranges. X will go from 7 to 9, Y from 3 to 5, W from 2 to 4. The error tolerance delta will also be set to 5.32 in minus 15. We have compared our tool FERA to 3 other tools, FPTailor, Precisa, and Fluctuate. In the table below, you can see the over-approximation of the error computed by each tool. Note that all bounds are smaller than delta, except for the one computed by Fluctuate. This means that no alarm will be raised for z less than or equal to 10 over reals. In this case, Fluctuate raised a false positive. This means that it thinks that the alarm can be raised, whereas in practice it is never raised. Remember that I've also told you that our tool FERA can compute an under-approximation of the largest absolute error. This is why we know input values for x, y, and w that can exercise an error on z. Such error is used as a lower bound on our enclosure of the largest absolute error. Here, you can see that both bounds of the enclosure are of the same magnitude, which means that you are not too far away from the largest absolute error and that you have a tight enclosure of it. So let's see how our solver manages errors. First, we need to be able to represent them. So first, if we consider a floating point variable of a constraint network, it has, as usual, a domain of values. This domain is represented by an interval of floating point numbers. For example, if you look at the x variable from the motivating example, its interval goes from 7 to 9. But such a domain is not enough to also represent errors. Thus, we created a new domain called the domain of errors. It is represented by an interval of rational numbers. Here we have an example of the interval representing the initial error of variable x. With this, for any floating point variable of a constraint network, we will have both domains, a domain of values and a domain of errors. So how will we go about filtering them? For the domain of values, we will use projection functions from a previous work by Claude and Michel. Those functions can manipulate floating point numbers to compute bounds and values, but they are not adapted to compute errors. Thus, we define new projection functions that are based on a formula to compute errors. This formula starts by doing the difference between the operation computed over reals and the operation computed over floats. For example, if we consider the subtraction constraint like z equal x minus y, we can compute the error of z by doing the intersection with its initial value and the expression computing its new value. This expression starts by doing the difference between the error of the operands, then add the error generated by the elementary operation. All those functions are defined for arithmetic constraints, namely addition, subtraction, multiplication, and division, and an assignment constraint where it will propagate the error from one variable to the other. The next step is to be able to express relation between errors. For this, we will use dedicated constraints. So let's go back to the motivating example. On the left, you have a piece of code that we analyzed earlier, and on the right, the model that we wrote and gave to our solver. On the first line, you have the objective function that will maximize the absolute value of the error of z. This is a constraint over errors, as it manipulates the domain of errors of a variable. Similarly, on the last line, you have a mixed constraint, as it involves both the domain of values and the domain of errors of a variable. This constraint states that the value of z over reals need to be less than or equal to 10. This is how we modelize our optimization problem. So now let's see how we go about solving it. For this, we use a branch and bound algorithm that does an error maximization directed by a search on values. This means that we will explore a finite search space over floating point numbers, thus guaranteeing termination. As I've said before, we compute an enclosure of the largest absolute error, where the lower bound E star is reachable and computed by a generate and test. The upper bound over line E is an over-approximation of errors that we compute with our constraint filtering. But finding the largest absolute error is hard in general, because we may need to explore large part of the search space, which can take a lot of time, and even resort to enumerate some of its values. Thankfully, we have an anytime algorithm, which means that we can stop it whenever we want to, and still get the enclosure computed so far with input values exercising the lower bound. Still, arbitrarily stopping our algorithm is not a good idea. So how to improve solving time and still compute good enough bounds? For this, we'll use a property of our error modeling. This property states that the operation error is always less than or equal to half a ULP, that is the distance between two consecutive floats, of the result of an elementary operation. Such a bound is highly dependent on the distribution of floats, as they are more densely packed around zeros than toward infinities. Now, let me use an example to show you how we improve solving time. If we consider the open interval I going from 2 power n to 2 power n plus 1, we know that for any floating point number inside the interval, its ULP is constant. This is true because for any two consecutive floats inside the interval, the distance between them is always the same. Thus, we cannot improve our operation error bound with filtering only, and may even need to enumerate values inside this interval to reduce it. From this, we can state a new criteria to stop our solver. We will stop exploring a subspace once all operations are reduced to an interval I. We will call such a subspace a signed line box. Note that a signed line box is still a valid box that may contain a solution. We just do not want to further explore it because it will take a lot of time. Cutting such subspace from the search space will allow us to reduce the solving time dramatically while still computing good enough bounds. Now, let me go over the main steps of our algorithm. First, for the bounding part, we compute our over-approximation of errors by first propagating all constraints to filter both domains of values and domains of errors. Once we reach a quasi-fixed point, we'll update our upper bound by taking the maximum values between the upper bounds of boxes left to explore, or the local upper bound of the box we just filtered, or the maximum bounds of the signed line boxes. Once it is done, we now have the best over-approximation we can compute at this time. And we now can go to the lower bounding part. As I've said before, it is the reachable errors that we compute with the generate and test. So first, we do a random instantiation of input variables with respect to their domain of values. After this, we can consider a function f that represents all the computation done inside the program we want to analyze. We will do an exact computation of this function over rational numbers, and a machine computation of this function over floating point numbers. Doing the difference between the result of both functions will give us a reachable error. Now, before doing another random instantiation, we can use a local search to improve the computed error. This local search will be guided by the best local value of the error. We'll compute the new error by also doing the difference between both functions. Finally, once the whole process is done, we can update our lower bound with the greatest computed error so far. We'll also save input values that can exercise this error. With this, we have now computed both the lower bound and the upper bound of our errors, and now can go about the branching part of our algorithm. So first, we will choose a variable and do so in a round-robin order to equally explore the search space. A variable will be chosen if and only if its domain of values is not reduced to a single value. After this, we can split its domain of values with a bisection, generating two subboxes that will be added to the list of boxes to explore. Finally, we need to select the next box and use the best first search to do this. We will choose the box with the greatest upper bound of the error, as it will give us more chances to compute a better lower bound. This is how our algorithm computes an enclosure of the largest absolute error. So now let's see how well it compared to other tools. For the experimentation, we have selected benchmarks from the FPBench suite, a common standard of floating point error analysis. You can see the full experimentation table inside the paper. For the lower bound E star, most of the time we compute better bounds than best known values, whereas for the upper bound over line E, our tool classified best twice, second 8 times, and never computes the worst result. Note that both bounds are almost always in the same order of magnitude, which means that we are not too far away from the largest absolute error, and that we compute a tight enclosure of it. Also, solving time is reasonable and compare well to other tools. Now, let me conclude this presentation. We've presented an algorithm to compute a rigorous enclosure of round of errors, where we have a reachable lower bound, as we provide input values that can exercise the error. We also compute a tighter enclosure of the largest absolute error that can help us remove some false positives, as shown in the motivating example. Further work will include the tighter representation of round of errors for elementary operations, and we will also do more experimentation with the different search strategies, from constraint programming overflows or from other constraint reasoning techniques. We'll also work on a more efficient local search to not only compute a greater lower bound, but also speed up the overall solving time. Thank you for listening. I will be happy to answer your question at the conference.